Hello, everyone. Good afternoon. Welcome to the fifth lecture of the workshop of PWF Sudan Expanding Horizons in Physics in Sudan, the second edition. Density Functional Theory Methods and Applications. Today's lecture will be given by our distinguished speaker, Professor Andrea Schleife, affiliated professor with the National Center for Supercomputing Applications and also the Materials Research Laboratory at the University of Illinois. Prof. Andrea, he's a member of the executive committee of the African School for Electronic Structure Methods and Applications. Prof. Andrea, he is a leader of a group which uses advanced computation to understand and predict materials properties for electronic and energy applications and under also extreme conditions. So please welcome Prof. Andrea Schleife. The stage is yours, Professor, and you can share your screen, please.
Excellent. Thank you. Thank you so much for the introduction. Now let me just try to find the window again. Okay, so I'm doing my writing test one more time. You guys see what I'm writing?
Yes.
Excellent. Perfect. Good. So welcome and thanks for taking the time to participating. I like very much that people are interested in electronic structure and people want to learn about electronic structure because it's an interesting topic, and it is also a topic that's currently changing. You probably have seen that with AI, so intelligence, how we run these simulations that you are learning about right now, they are changing, and also the type of the sort of like the mathematical description that we're using is also changing. And so it's nice to start where you guys are starting, which is the electronic structure theory behind what techniques like AI are using nowadays. So we'll see. We will not talk about AI in this presentation, but if you are a user or want to be a user of electronic structure, you can absolutely learn the techniques today and during the school, and then you can use AI to run such simulations with simulation codes that AI is controlling for you or starting for you and analyzing for you. Okay, so before I actually get to the presentation itself, I wanted to briefly mention the work that you will hear about, and let me double check if you see I think you see this highlighter here. So the people who do the work in my group are, of course, the people on here, right? So I could not do the research that we're doing without my students. So these are the ones who are doing all the simulations. And today I will not talk about slides with results very much, but I will talk about at least briefly what my group is interested in. So in particular, I'm saying this because we are also looking for PhD students. We're looking sometimes for postdoc scholars in my group. And so I want to just give you guys an idea of what we're roughly working on. And I think since ASESMA in Rwanda, that is again a couple years ago, but since then we are now looking at three different, I would say, branches of electronic structure that we're doing in my group. The first one, and I'm almost sure I did talk about this in ASESMA in I think in 2023, it was 2023, is related to electronic and optical properties. So I will not talk about electronic and optical properties today in the presentation, but what we're interested in my group is we would like to study optical spectra. So for instance, what you see here is a pump probe spectrum of a material. And as you can see, as we change time, so the time that we're looking at is fast. So here, for instance, you see a time scale of picoseconds. So that's fast. And we would like to simulate the spectrum. So the spectrum you see here, maybe I can zoom in here. This is the dielectric function. I don't know if we will discuss this in the school, not today in any case, but this is a quantity you can think of as optical absorption. So that's an experiment that you can perform. So we measure a spectrum at each time step. So we do many of these spectra. We stick them next to each other, and that gives us a picture that looks like this, and that is a pump probe spectrum. My apologies. So that is one of the simulations that we're running in my group. We're also looking at time-dependent density functional theory. So this is a procedure. You will learn about density functional theory in more detail here, and there is a time-dependent version of it. Okay, so even today we will talk about density functional theory in a static point in time. So we take snapshots, like with a camera, we take one snapshot, next snapshot, next snapshot, and at each snapshot, in this class today, the electrons are in their ground state, but they don't have to be. So if you have a solar cell, for instance, or a laser, the electrons can be in an excited state, and that causes time dependence of the electrons, something that we would like to simulate. And we're looking at disorder, which in this case is temperature. So if you have a material at a non-zero temperature, temperature causes the atoms to move. We will talk about that today a little bit. And that causes disorder. And this is either temperature can be one of those factors that cause disorder. It can also be an alloy. So we make a material that has disorder built in. So that is one of the things that we're looking at. I'll send you, I believe I can send you these slides after the presentation also if you want to look in more detail.
Thank you.
Okay. Then the second part, and that is maybe more new in my group. I think it just, maybe, I don't even know, maybe in Assessma when I was there. So I couldn't make it to Ghana, but I was in Rwanda 2 years before. And I believe this was not even published yet at that time. I think maybe we talked about it, but it was not published. So what we're now trying to do in my group is we would like to reduce the computational cost that these techniques bring. So running such simulations takes a lot of computer time, and to reduce the time that we run on a supercomputer or on a simulation computer, we would like to reduce that time, and we do that in my group by trying to replace some of the simulations with machine learning or with artificial intelligence. So for instance, we're not going into the details in this presentation, but we can look at radiation in a material. So let's say we have for instance a semiconductor, and we're shooting a proton into the material, so it moves as a function of time, and we would like to simulate that and how the electrons are responding and things like that. And again, disorder. We also would like to use machine learning for disorder because so maybe I go briefly here. So a simulation cell on the order of maybe 16 atoms we can do with density functional theory, but the problem is the cell is too small, so we need more atoms. But if we go to larger and larger simulation cells, then those are so many combinations that we cannot do that with DFT anymore because it's too many simulations. And so we use ML machine learning for that, for instance. Again, I will not discuss this in detail. And the last one is, and that is very new, I would say. I have actually no real idea yet what exactly we will do there, but something that we're currently, we have a chance to explore is quantum computing. So nowadays, companies have quantum computers that we can use. We can also simulate them on classical computers, and we would like to explore how and to what extent and for what type of problems is a quantum computer useful, so that we can use a quantum computer instead of a classical computer. Okay, so this is the most recent addition to my group, and we have maybe currently, I think I have 2 students working on that. So this is something where we really have to learn a lot, and I don't have many answers yet, but we're at least exploring. Okay. Anyway, if you're interested, you can either check my website or you can always send me an email if you want to, we can meet after and talk more. All right. So then let's look.
Uh, Andre,
Go ahead.
quick
Yes.
question.
Yes.
So about when you say disordered system, what level of disorder is it? Like a defect or atomic structure
Good
disorder
question. So
or
So disorder in this example, it is an alloy. So I can send you again. I should have put references here. This is published. So we have an alloy. So this goes, for instance, this is cadmium selenide. So it goes
Mhm.
from, sorry, cadmium sulfur selenide. On the left-hand side, it is cadmium sulfide. And on the
Mhm.
right-hand side, it's cadmium selenide. Sorry, where's the, sorry, here. So here it's cadmium sulfide, here it's cadmium
Mhm.
selenide,
Mm.
and somewhere in between. So it's an alloy, and
Okay,
and then the disorder comes from uh, atomic occupations of sites with atoms in the simulation.
interesting. Yeah, the above picture look like beach and oceans, like the
Yes,
evaluation with time.
yes.
It's really okay. Cool.
So what you see here is an optical spectrum again. So we're looking at optical spectra, and in what the disorder changes is it moves these peaks around. So for instance, if you're looking at the band gap I think is somewhere here, and the band gap is zero everywhere where it's white. So this is, let's say, this is where it's zero, but the band gap changes, of course, if you change the composition of the material,
Yeah.
the band gap changes precisely. And so this happens. So the band gap is here at the onset, but at higher energies, other peaks change their position, and and that causes these waves. I agree. It looks a little bit like ocean waves. I agree.
Okay. Nice. Thanks.
Yeah. The other disorder, and you will see images today for that. The other disorder is phonons. So when you have a material, even so, no alloy. Let's say we have, I don't know, some material, iron, let's say. Um, and you do that at 0 Kelvin, we're going to put the atoms at their equilibrium positions. So that's where they want to be at zero temperature. But if you have now, let's say 300 Kelvin, so room temperature, the atoms can move around, and that causes this disorder. So I'll show you maybe that picture later when we get to it.
Okay. Thanks.
Good. Great. Okay. So then maybe we should look at the actual lecture. So what we want to talk today. Okay. So normally in my group, I would say we use these techniques a little bit. No, now we're not necessarily experts in developing the techniques, but we're using them for simulations. And so what you see today, all these techniques are implemented in density functional theory codes. So if you run Quantum Espresso, if you run VASP, if you run any of those packages, they have these techniques that we're talking about today. They have that implemented in the code. But I will start first. What do I mean by forces? What are the quantities that have these forces, and so on. So we'll start very simple in the beginning, and then I'll show you some slides about practical simulations in a DFT code. And then maybe you guys can ask some questions. So let's see how that goes. Literature. So I did actually, I used this from these specific papers. If you don't find them, I'm happy to share them. I forgot to put the reference, the exact, the exact reference here, but just let me know if you cannot find these papers. This is a book. This is Richard's book, of course. And then this is a nice book about, it's a nice paper about molecular dynamics. And then this is an electronic structure book. So let me know if you cannot find it, and I can point you where it is. Okay. And then thanks to our local materials research, science and engineering center. All right. So let's do a very simple start. And I hope you guys are answering questions on Zoom, so we'll get to that in a second. So what I would like to know, when you hear the word forces and relaxation, so what entities? So what entities do we describe? So what are things that we're interested in to describe forces in between? So like between what? Between which entities? So what forces are you guys interested in this class? Not general, but in this class. So let's
Electrons.
sorry, say one more time.
Electrons.
Electrons, very good. Okay, so let's draw. How many do you want? How many electrons should we look at?
You mean
Like
how
five?
many electrons?
Yeah, like five? Well,
We can start with two. Oh, maybe, yeah, maybe. Put in five.
two,
Five is okay.
five. Okay, let's do five. 2, 4, 5. All right. So I make the negative sign in here because these are electrons. Okay, so if that was, this is what we, if that, yeah, okay, so that's a good starting point. So we will need more ingredients here. And the reason I'm emphasizing this so much is because we will treat the electrons and another entity completely differently in practice. And I would like to talk about this first because some of you guys just learned to, started to learn quantum mechanics. And so I want to make sure that if you were to write down these equations yourself, this is how to think about it. All right, so we have electrons here. Now, what else? Do we have anything else? So they have forces in between, yes. I'll come to the forces in a moment.
Between nucleus and electrons.
So say one more time. You did what?
Between nuclei and electrons.
The electrons we have. So these are the electrons. So what's the other entity?
The nuclei.
Nuclei. Yes. Perfect. Yeah. All right. So now, excellent. So let's look at nuclei. So the electrons we have here, I make those maybe blue. Nuclei.
Also, if we consider the atomic density, we can the electronic density.
The electron, okay. So I'll write those quantities here for now. Because we will. So electron density. Okay. Good. Yeah, that's good. We're getting there. So let me draw a couple of nuclei. For nuclei, we have to now be careful because I'm going to start with the most simple nucleus that we can think about. And that is which one?
One proton, one neutron.
All right. So let me just, before I go there, Roa Kedir. So Roa mentioned, for instance, quarks. Absolutely true. It's a subatomic particle, but and I believe people use density functional theory in some version to describe quarks. Now the problem is when I say I believe, I have no idea about quarks. I've never looked at them, and I think the last time I heard about quarks was when I was a student. So I'm not working with them. They are in nuclei. They are inside of the nuclei, and there is forces in between, and people describe them. But the energy, and maybe that's an argument that I'm going to use here. So the energy between quarks is very, very large. So the energy is so high that we don't have material science or condensed matter physics at that energy scale so much anymore, and it's subatomic. So it is really inside of the nucleus and things like that. So in this lecture, we're not going to talk about quarks, but absolutely one of the entities that people use, for instance, quantum mechanics for, absolutely, and is necessary. Okay, good. Sorry, and then another person said something, and I didn't hear it.
You asked about the simplest nuclei, and I answered that it's one electron, one neutron.
That's right. One
proton.
Exactly.
One proton.
Don't worry. This is good. That's exactly what we're talking about. No, because in the end, forces, to understand, the forces between which is actually happening here. That's why I want to have this starting point. Okay, so perfect. So let me just close my chat again here. So here's the chat. Okay, so the most simple nuclei are protons. Okay, so let's do, for instance, like this. I also do 5, and I'm doing 5 because in a piece of in a material. So in this case, this would be hydrogen, but you can take any material with more electrons and with higher Z numbers. Typically, we have equally numbers electrons and electrons and positive charges. All right. So this is maybe these are entities between we have forces. Perfect. So when we are looking at this today, this is a good starting point. The only more difficult part here is typically we as condensed matter physicists and maybe also material scientists, we're typically looking at heavier atoms, so like maybe iron or silicon or carbon or things like that. What you see here is just hydrogen. Okay, but that's not a problem. All right, so then this is what we would like to describe. So now you could look at this picture and you could already ask the question, what forces are there? So you have these guys here. So what forces are the ones that we are interested to describe? So let me find a different pen. So what force do we now want to describe? What force are we interested in?
Column repletion.
Mm-hmm. Coulomb, exactly. So
Electrostatic
this
force.
is because, sorry again?
Electrostatic force.
The electric force, the Coulomb force. Sorry. Well, one person said something and I think disappeared now, so I'm not sure. But okay, so the force that we're interested in between these charged particles are Coulomb forces. So let's write that. So for instance, there is a force in between these guys. I'm gonna make those here for now. It's all the same. So the Coulomb force, exactly. Now, Coulomb force is important here simply because the way we describe both electrons and the nuclei, those are charged particles, and the force that is dominant. So the other forces that are there is, for instance, gravity and things like that, but those are much, 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 much smaller. And so the force that we need is Coulomb. Okay, so I'm going to write that down here. So this is the Coulomb force. All right. Now, does anyone have an idea what the Coulomb force looks like as an equation? Like the equation of the Coulomb force. I'll let you guys write that or say it maybe. What does the Coulomb force look like? No. Any guesses? What does the Coulomb force look like?
Q1, Q2 over R square.
Perfect. So I'll keep it short. So we have, yes, so charge 1, charge 2 over R square, for instance. Exactly. All right. Perfect. We will use that in a moment. And maybe I'll show you what it looks like. I'll draw it in a moment as an image. We'll get there in a moment. Perfect. This is the force that we're interested. Now, the problem is, and I think that's what we'll deal today with, is in this picture, I said there's only a Coulomb force between these two guys. In reality, of course, there is more forces. All of them are Coulomb, but you have also forces between these guys. You have forces between these guys. And that is true for all of these guys. So I'm not drawing a lot more because there's too many, but we have Coulomb forces between all of these different electrons and all of the different nuclei. Okay, so that is really what we need to account for. All right, so let me see. There's a question in the chat. Oh yeah, exactly. Perfect. Yes, you guys can always if you put it in the chat, I will every now and then look, but you can also just say it if you want. Good. So this is the Coulomb force. Now, we have already sort of a picture what we would like to describe. The other question is, so how do you think we now will describe this? So what equations are we going to solve to describe what these electrons and nuclei, what they are doing? Like if you want to compute their ground state, for instance. So what equations do you have to solve? And that is what you guys discussed, I believe, with Michele maybe on Tuesday. What equations do you have to solve? So I'm going to write that here.
I think
Yeah.
Hamiltonian.
Say what again?
Hamiltonian.
A Hamiltonian. Yes.
Schrödinger
Very
equation.
good. Perfect. We'll do that in a moment. Absolutely correct. Hamiltonian. Okay. What else is there? So is that everything, or like in practice? Again, think about it, what you do when you run such simulations. So we have to solve a Hamiltonian. Absolutely. What else is there that we have to solve?
We have to take the summation of all entities.
Yes. And what do you do for all the entities? Sorry, sometimes the audio is a little.
We have to take the summation. The summation.
Yeah. So and how would you do that? Like how would you actually, like what would you write down?
We have to take the summation of all interactive entities.
Yes, exactly. And so I agree. And so the way we will do it in this class, the way we're going to do that is we're going to solve a Hamiltonian for electrons. And in this class at least, and I think that is true for most, if not all, almost all of the density functional theory simulation packages, so electronic structure codes, they also describe the nuclei, and they do classical, so F equals ma, so classical nuclei. Okay, so I'll write down more equations in just a moment, and you'll see exactly what I mean by that. But what you guys, as people who have just started with quantum mechanics, what we're going to do is we have to solve a Hamiltonian for the electrons, and that's what we then use. So somebody says electron density and things like that. So that all comes from this Hamiltonian, and that is for the electrons only. So only the black one guys here, these guys. And for the blue guys, we do oftentimes classical F equals ma, so Newtonian equations only. Perfect. Okay, so this is a good starting point. So electrons will treat quantum mechanically. So in principle, we could also treat electrons classically, but that description oftentimes is very bad, so we're not going to do that. And nuclei, in this class, we will do it classically, but in principle, you could also do that quantum mechanically, but that makes it very expensive. So the downside of treating both electrons and nuclei together in quantum mechanics is possible, and people do that, but very few people do because it's very expensive. So it takes a lot of simulation time, and it makes the description very complicated. So that's why we typically use this here. So I'm going to say like this here. So here we use a Hamiltonian for the electrons and classical dynamics for the nuclei. Okay, perfect. So now let's say, and I think somebody talked about Hamiltonians already. So let's say we start with the electronic problem that we would like to solve. All right. This is how I teach quantum mechanics to our students. So if you have a quantum mechanical problem that you want to solve, you can always use this 3-step procedure. Works always, is sometimes super complicated, but those steps are always the same. So how do we do how do we solve a quantum mechanical problem? So we start by writing down the Hamiltonian. All right. So anyone, do you have any guesses what the Hamiltonian looks like in general? We make the Hamiltonian specific for this in a moment, but before we go there, what does the Hamiltonian look like? So I'm going to write H. So what does the Hamiltonian look like? What terms are in?
Potential energy.
Potential energy, yes.
And kinetic
Okay.
energy.
And the kinetic energy, perfect. So excellent. This step, every time you solve a quantum mechanical problem, you do this. You did that with, I believe, with Michele. So this is always how you start. We can look at all sort of systems. We can look at we will look at a couple of systems and different Hamiltonians, but this is always the starting point. Okay. Now I should say this step is typically the easy step. So meaning you guys have to decide. So the kinetic energy, it's always just the kinetic energy. You just write down that term, and then you have to decide what is my potential. That may or may not be a little bit difficult, but in principle, this step is the easy step. Okay. Now, the second step is, after you've done this, we're going to solve a Schrödinger equation. All right. That is the very difficult, if not impossible step. Okay. So solve Schrödinger equation. Now, what do you get if you solve a Schrödinger equation?
Psi, wave function.
Excellent.
Wave
Exactly.
function.
That's perfect. Somebody says energy, somebody said energy, and the wave function. Exactly. Perfect. You get the energy, you get the wave function. Excellent. If you have the wave functions, you can then, for instance, turn that into an electron density and so on. We get that later, but this is exactly what you have to do. Go ahead. Okay. I don't know if somebody said something. If you said something, just say it again. Otherwise, I'll continue. Okay. So yes, we compute that. This step, super difficult. So in practice, it's so now when I say difficult, you can describe that in different terms. So for instance, you can say, well, the mathematics is very complicated. And if you learned quantum mechanics at some point, maybe from Michele or maybe from someone else before, solving the Schrödinger equation with pen and paper, mega difficult, if not impossible. So that's already difficult. And on top of it, even if you solve the Schrödinger equation numerically on a computer, still mega difficult because the computational cost, so the amount of computation that you have to use to get a solution of the Schrödinger equation, increases exponentially with the number of electrons. So if you guys can solve a Schrödinger equation for 2 electrons, that's great. And I think people have done that many times. But if you have, for instance, 200 electrons, essentially impossible. And if you have 2,000 electrons, it takes the not quite the age of the universe, but it takes super long. And on top of it, storing, like saving the wave functions, for instance, to store them on a computer or on a cluster or save them on a hard disk, also exponential. So meaning if you have something like 26 electrons, you use more storage than exists in the entire world to write down that one Hamiltonian, like the wave function. So this kind of stuff is the problem. So this is the difficult step. And for this, we will make approximations. Okay. I'll tell you in a moment. There are many different choices. We will in this class, we will use density functional theory. You can use other things, but you need approximations here. So I'm going to write that here. So we have to approximate. Okay. And then today, I think we will actually not really do this step, but in principle, once we have the wave functions, you can compute expectation values of operators. So for instance, I'll ask you one example in a moment, but if you're interested in quantities that people measure in experiment, that means you have to compute an observable and compute the numerical value of that observable you have those numbers, and then you can compare, for instance, to experiment or use them for other types of simulations. Perfect. All right. Now, any guesses? And that's maybe the last question for this slide. So, who has a guess? What is the most easy observable that we will need in this class today?
Electron density.
Say again?
Electron density.
The electron density, we will not need, we don't use it as an observable so much. No. What is even simpler? It's already written on that slide.
I think momentum and total energy.
Momentum is an option. Absolutely. We will also not
Energy.
really compute it today. Say again?
Energy.
Energy. Exactly. That's exactly what we need. So today we will really only do this, and then we have the energy, and from the energy we go to forces. That's it. Okay, perfect. That's exactly where I want to get with this. All right. So now the other thing, we are interested. So in order to in order to get to forces, you can use exactly this same. This is sort of like a summary slide right now. So we already said today we're going to treat the nuclei classically, and we treat the electrons quantum mechanically. That's what we do today. What we want to know is we want to know the forces between atoms. Sorry, between atoms. That's what we would like to compute. So this is sort of like, that's what we want. That's what we're interested in. And we can do something like, so in principle, we could do this, right? We could use something like 5 hydrogens. We will start with the simpler case. And I'm actually interested to see, what do you think is the most simple, the most simple case where we are looking at forces between atoms? What is the simplest system that we can come up with? So we want forces between atoms, and what is the simplest one? Where we have
Hydrogen?
no, but which system? Yeah, so the energy we will absolutely need the energy, but what is the system that you want to like? The system that the material, if you want.
That solid, you mean?
No, but so how many atoms, how many electrons is the simplest example here for looking at
Neutrons?
forces between. Say again?
Neutrons?
Neutrons are, we ignore neutrons in this lecture today. So
Atoms.
let's build it. Let's start from the screen. So let's say so in one electron. So let's do this. Yes, one electron. Okay, we could start with that. The problem is the electron is all by itself. There is no force between anything. So we need at least one more entity. We're interested in atoms. So I'm going to draw my proton again. All right. Now we have one atom, a hydrogen atom, and we can look at the force between that. But we're interested in forces between atoms. So this is not enough, because we need a second atom. Otherwise, we have no force between atoms. And for that, we need another proton. That is the simplest case that you can come up with if you're interested to understand forces between atoms. So this is a neutral proton, a neutral atom, so a proton with an electron. And this is just a proton, so this is not neutral. But in some sense, you could say, I take a hydrogen atom, and I take another hydrogen atom and steal its electron, and that system has a force in between. Okay, and so now I'm going to make that maybe like this, because what we're interested in over here, we looked at all the forces between all the different electrons and nuclei. What we're interested now is of forces between atoms. Okay, so this is the force between the atoms in this case. So let me see if I have said anything. Yeah, we want to look at forces between atoms. We need at least one electron and two nuclei. So I'm going to write that down. One electron, two protons. That's the simplest case that you can come up with. And then we can use our three-step procedure. This guy here, we can do that, right? We have now, this is our system that we want to describe. You go back here, you say, I write down the Hamiltonian and the Hamilton operator, and then I solve the Schrödinger equation. Okay, you can do exactly that for this. So we use our sort of like this three-step procedure. I would call that here, three-step approach. Perfect. All right, so let's see if I forgot anything. I said this. And the energy, okay, and the observable, okay, so let me see. Maybe I make a little bit of space here. Yeah, like this. And then the observable, you guys already said it, energy, perfect. Let's use the energy. That's exactly what we need. As observable. Excellent. Let me just check what you guys said. Okay, so electromagnetic is so Roa wrote electromagnetic. I'll come to that on the next slide. So just in a moment. All right, perfect. This is it. So this is the simple system where we're interested in forces between atoms. All right. And then let's see if I forgot anything. Okay, so and then we write down the Hamiltonian. So in other words, we start with H psi equals each energy times wave function. Perfect. All right. Excellent. Now, if you're bored or uninterested by this sounds so simple and we don't really care about that, I agree with that in principle, but it's at least a starting point because on the next slide, we turn this into a Hamiltonian that you can use for any material that you're interested in. All of the materials have the same Hamiltonian. So let me see, why can't we use one electron and one proton? Okay, good, raw, excellent question. We can only do that. But why cannot we not use this, and that's it? We can, but this is only one atom. And on this slide, we're interested in forces between atoms. So if you have only one atom, that's it. That is the force that atom F itself experiences no force like a neutral hydrogen. This is a neutral hydrogen. Super happy, has no forces, it just sits there. Okay, perfect. Ask these questions. I want these distinctions are important because otherwise it's not clear why are we doing this. So that's why I ask these questions. It's perfect. All right. So what I'm gonna do here maybe is I'm gonna cross this out because we're not looking at that. We need at least two atoms. Perfect. All right. So now let me close the chat again. If you're now interested in and saying, okay, this is too simple, and I want to do iron. Somebody asked about solids and things like that. Absolutely true. Let me see. I think that's already what I wrote here. I think I wrote that already. This slide is, this one is the one I meant actually mean. Okay, so now, what does the Hamiltonian look like if you're interested in solids, for instance, or any system of material science, or condensed matter, really, for that matter? This is the Hamiltonian. This Hamiltonian is true for each and every one of you guys because it's the Hamiltonian that we always use. So now let's walk over that real quick. So we start with electrons. So here we start, maybe I'll make this red. Okay, so we start with electrons. Now, in our system here, we had only one electron, so our Hamiltonian became very simple. In practice, if you have iron, for instance, you have 23 or I don't know, 26, I believe, is this electrons in this case. The thing is, you simply write the kinetic energy. So this is the kinetic energy of the electrons. And you have one of these terms for each electron. Okay? If you have only one electron, then it's only one times this term. If you have a material, magnesium oxide, and you have maybe, I don't know, 50 electrons, let's say, so you have a sum over 50 such terms. Okay? You write all the kinetic energy terms of the electrons. And then we have, this is actually what we wrote here, these guys, the interactions between all the electrons, all these terms that you see here between all the electrons, like this and so on, is exactly this. Is the Coulomb interaction between the electrons. So this is the, so I'm going to write, so the Coulomb electron interaction. And you do that. Same as here, sum over all pairs of electrons. In our case, we have one electron, so it's only one term. Like there is no electron-electron interaction in this case here. But if you have a material like magnesium oxide, you have to sum over all of them. Perfect. So what other terms are there in our Hamiltonian? The next term is the electron-ion interaction. So that's a potential energy term, and it's the Coulomb potential still, because the nuclei are positive and the electrons are negative, so it's still Coulomb potential. And we have a sum over all the electrons and all the ions. Okay, if you have only this example here, we sum over one, we have one electron and two nuclei, so then you have only that here, but you write those terms here. Okay, that's the electron-ion interaction. So I make those purple because it involves both electrons and also the ions. All right, so this is the electron-ion interaction. And then, now we have a choice. Either we treat our nuclei as quantum mechanical particles. If we do that...
Sorry, Prof. Andre, I have a question.
Yes. Go for it, yes.
As we know, electrons have very, very, very high speed. And my question is how these non-relativistic equations describe the relativistic system.
These are non-relativistic. I agree with that. So in this case, it's non-relativistic. You could have a Hamiltonian that includes, so I'm going to write it here, okay. We would have to include relativistic effects. We don't, in this Hamiltonian, there is no relativistic effects. Would have to include so for instance, we could solve a Dirac Hamiltonian and stuff like that. So yes, there are equations for that. This is Schrödinger only. We're not doing a Dirac formalism. You could do that, but not in this class. Excellent question. Very good question. Okay, so let me just go back here. So we would have to decide, do we now want the ions to be quantum mechanical or not? So in this picture that you have on the slide right now, the electrons, the nuclei are treated quantum mechanically. And you can do that simply by saying we have a kinetic energy of the nuclei and we have a potential between the nuclei. You can do that in this class, and for today, we're going to cross this one out and we treat them classically. So this is not generally true, but today it's true. So when we do DFT, in particular when you do density functional theory, we oftentimes do not treat the ions quantum mechanically. So today and in DFT codes, ions are classical. They are not quantum mechanical. I think I said this on the previous slide. So that's why we cross out the term of the ions. All right. And then the last thing is somebody, I think Roa asked on the previous slide about electromagnetism. So for instance, a strong laser, an electric field, stuff like a magnetic field, things like that. So other fields, other external fields, they exist, and we could have to write them down also. In this class, we're also not doing that. So in this case, we assume we have a material that is not in an electromagnetic field. It just is, you have a material without such a field. So it's because it's an external field. So the internal Coulomb interaction is of course included, but there is no external field here. Okay. So I'm going to cross those out as well. Not for today. It is possible that you have to include them if you want to describe a material with an electric field or with a magnetic field or with an electromagnetic field and things like that. All right. So this will be the Hamiltonian that we have to deal with in this class. All right. So at this point, I think this is a good, we now have to look at some solutions here. So far, we only have looked at the Hamiltonian of the electrons. So far, by the way, we have not really computed the forces between the atoms. We have to get to that. Any questions that you guys want to ask? I think other than that, we move on a little bit. So this is what we would like to describe. So this is the system here. We start with that. Or more electrons or more ions. That's fine. Then the Hamiltonian looks like this. All right, good. Okay, so now what do we actually do now with this? So summary, we have the simple system. We have multiple nuclei. So the simple system is the H2 ion. That means we have 2 nuclei, 1 electron. I think I said all these things just a moment ago. And we want to do an exact solution from a Schrödinger equation in 3 dimensions. So what we would have to do is, in our case, would be the Hamiltonian is the electric kinetic energy, the electronic kinetic energy, plus a potential between the 2 nuclei. And then we have so this is the ion 1, ion 2 interaction, and then we have the electron ion interaction between nucleus 1 and nucleus 2 with the electron. So this would be a Hamiltonian that we could solve. Okay. Let me just see if I have a slide. Yes, I have a slideshow. That's good. Awesome. Perfect. And so now you could try to solve this mathematically with pen and paper. I think that is true. The thing is, this equation is already too complicated to solve exactly with pen and paper. So in practice, we're going to solve that with computers. And so what we're going to do in this class, because this is a pen and paper class, so we're going to solve this, and we make some simplifications. The first thing is we're only looking at 1 dimensions, and so that gives us a simplification. And then we're going to make 2 approaches to describe the potential. So I'm going to write that here in a moment. But the Hamiltonian itself, or the Schrödinger equation, I should say, looks like this. I'm going to write that here once, because you have seen this probably with Michele. So this is our kinetic energy. Hold on, sorry, I think here we go. I hope you still see my pen. And then we have the 2 terms for pi. So this is in SI units, but that's okay. Minus. So this is the Hamiltonian 4 pi epsilon 0 RB. So that's in principle the Hamiltonian we have to solve. And then you guys talked about Schrödinger equation. So we have a wave function, and that equals energy times the wave function. So this is what we would have to solve. Okay. Now, we will do this at least in a picture. before we're going to go to this, we're going to make it a little bit simpler again, simply because we can solve that by writing it. And so what we're going to do is we're going to treat our potential like this. We're going to do a well, oh, sorry, wrong pen. Here we go. A well potential. Instead of using a Coulomb potential, we can make a quantum well potential, so an infinite well. And I'll ask you in a moment. So who of you guys have solved a potential of an infinite well? Did Michaela do that with you guys? You guys can chime in here. Did any one of you guys solve infinite well before?
I didn't.
You guys did? So who did not yet? Solving a potential well, an infinite potential well.
I think
In one
most of
dimension.
the
You did?
participants,
Oh,
most of the participants did in the mechanic in the
perfect.
bachelor degrees.
Perfect. So this will be what we're going to do is we know in principle we want to solve this one, but you can already see that this is more complicated to do that, analytically, and we're going to do that with a computer in a moment later. But what we can make it simpler, if this is too complicated as a potential, I would agree with you. I also don't know how to solve that with pen and paper. And so that's why we start with a quantum well. So quantum well looks like this, and we need, okay, so how many quantum wells do we need? So we want to solve this. How many quantum wells do you think we need? I go back to this one. For this equation. How many? Oh, here somebody is typing. Hold on, sorry. I always have to click the chat. 2, perfect. Mohammed, excellent. That's exactly it. All right, so let's go here. We're going to have 1. So I'm going to make the potential. This is the potential. And now we have, so then there's another well, and we have another like this. Okay, that's exactly what I'd like to solve. So let me maybe color this. So everything I'm coloring here, this is this and this. This is where the potential is infinity. And inside here, we say its potential is 0. Okay, that's the problem that we want to solve. So you guys started with quantum mechanics. This is not quite the most simplest Hamiltonian. You typically only look at one of these. But if we want to study, forces between atoms, so we need 2 of those wells, and this is exactly what I drew here. Okay, this is exactly what we want to solve. All right, now solving that is already complicated, and so that's why we're going to do that numerically. And what I'm going to show you, I will send you that link after. I just need to share my other desktop here. Sorry, hold on. I think this one. Do you guys see our Schrödinger solver here?
Yes.
Perfect. Okay, so what you see here, I can briefly turn this on. So, okay, what you see here, this is the electron density. You can see the wave function here. The wave function has a complex phase, so that's why it's oscillating in time. This is a single well. Now, what we want, and I sent you this link, we want 2 wells. Okay, so it looks like this. Well, potential is 0, potential infinity over here, potential infinity in here, then it's 0 again, and here it is infinity again, and then we do update, and this is what you get for that. Okay, so in other words, as you can see, it's not exactly symmetric. This is probably because I didn't draw it perfectly, but we have our 2 wells. So in other words, we can solve our Schrödinger equation here numerically. This code here solved the Schrödinger equation numerically, and that gives us the wave function. You see the wave function here in blue and in red. This is the complex wave function, and in black, the electron density. So that comes out of our Schrödinger solvers. And then we see also the energy states over here. Right now we're looking at the lowest energy state. You can also excite. That means we take it from this green level here to the next higher one. So let me click this button like this. So we are now here. So that is the next higher energy state, and so on. You can excite again. So then it goes to this state. Sorry, I clicked here. Okay, here. Now we're at a state that is behind this one, and so on. You can look at all the wave functions if you want to. We don't need that really so much. We are looking at the ground state, so this is what it looks like, and this is what the solution looks like. Okay, so this link, I'm happy to share. It's online, it's on GitHub. You already see the link up here. Okay, if you want to try that out yourself. All right, now let's go back to my slide. Okay, so this is the most simple solution we can do. And the solution that we then get is this one. So I took, just in case I don't draw it correctly, I took a screenshot beforehand. So this is what it looks like, okay, for a quantum well. So this is not such a bad approximation for approximating, well, either this or to approximate this equation, and we do not want to solve Coulomb equations. That can be complicated. All right, this is what the solution looks like. In particular, it gives us the wave functions, and it gives us also the energies. Also gives us the energy. Okay, perfect. Now I should say, before I take questions, I go to one next step. And what I'm going to do is essentially, let me draw. Hold on, I just need to find. Yeah, here. Okay, so that's what we just did. In principle, the next step would be, we don't want to just use infinite wells. We want to look at Coulomb potentials. Well, that makes sense because we wrote down here Coulomb potentials, right? We have to have that instead of these wells. We can do that. And the way we do that, I'm going to draw that here real quick. So we have an x-axis here again, just like we did before. So this is our position. We have a potential energy, and then we have, so our wells, I can draw these wells real quick. We just drew them like this. So our infinite wells are something like this, and maybe like this. If you want to make it more exact and you want to look at Coulomb potentials, you now have potentials. You have Coulomb potentials. So our potential maybe is more like this. And this. So blue are wells. This is simpler. And this is Coulomb potentials. And this is more realistic. Sorry, typo. And in particular, so this would be our wave functions that solve this equation. Okay, now let me just jump real quick to I'm not going to draw that with my mouse. I tried that beforehand. Again, this is a little difficult when you try out this tool and do this with your mouse. It's a little finicky to actually draw this, but you can do that. You draw your Coulomb potential, then space in between, and another Coulomb potential, and then you click solution, just like we did before, and you get, just like before, you get an electron density, and you get the wave functions. And then you can look at the ground state, you can look at the excited state, and so on. The idea is exactly the same. So let me look at your questions. And then we're almost done with, we almost have forces. What are the initial conditions? Do you have options? Oh, excellent question. Initial condition. So the initial condition, I mean, we are looking for the ground state. So initial condition in the sense that we're looking at a time propagation. There is no initial condition. If you're looking at the time dependence of these phases, that I mean, maybe I can go back to my, you saw these real part and complex imaginary part to fluctuate over time. That is the phase of the wave function, and you can choose any initial condition if you want to. I would say that's maybe my answer. I hope that answers the question. All right. So this is in your slides. I'll give it to you. What we have now done is the following. We solved the Schrödinger equation. And now what we want to do is, eventually, we want to look at forces between atoms. We haven't done that yet, right? So far, what we have done here is we solved the Hamiltonian of the electrons in Coulomb potentials. That's it. There is no force yet, and there's not even a change of the distance between the atoms. Any questions about this? So this is the, what we've done so far. Maybe I go to the next slide. So far, we solved the Schrödinger equation of one electron between two protons, of one electron with two Coulomb potentials. So that's what we've done so far. Any questions about this? Because now we're going to go to forces.
Sorry to interrupt you. There is a question on the chat.
Oh, hang on. Let me look at the chat. So I think I answered that. So the initial condition, so I wasn't fully sure what you mean by, so initial condition seems to imply there is a time dependence, and so the time dependence that we've seen is only this. So it's the time dependence of these phases, and we can set that to any initial condition, because the phase of these complex wave functions is not present if you compute an observable, which is a real function, and for the electron density, there is no time dependence in this case. So there is, it's an arbitrary initial condition. You can choose any phase that you want. 0 if you want to. So these are the phases. The time dependence. Time dependence comes from wave function phase. Wave function phase. We have no other source of time in this particular example. Please follow up if that does not answer your question. Okay. All right. So now what we've done is we solved the wave functions for the electron, and we computed the energy for this arrangement of for the arrangement of these electrons. So this is exactly what we solved. Now we go to forces. How do we do that? What we have to do is the following. So let's say we're plotting the energy that you get from the Schrödinger equation, from Schrödinger. And now what you can do is you have one parameter that you can choose. And what is the parameter that you have? I'm trying to jump here, this. One thing that you have is the distance between these atoms. This is not a force, this is the distance. This distance in this problem we held fixed. We said one proton is here, one proton is here, and we're solving the Schrödinger equation for this choice of the distance. Okay? Nobody told you yet how far are these two protons apart. Let me see, there's a question in the chat. How does increasing the number of the nuclei affect the energy levels and wave functions of the electrons? Excellent question. Well, okay, very good question. Imagine, this is the equation that you'll solve. Here we have one nucleus and another nucleus. If you have 5 nuclei, you just go here and say third, fourth, like so. 1, 2, so maybe I write it down here. So we could do H bar 2m, this, minus. And now I make it a little shorter just for simplicity of writing. This is the first one. RB is the second one. And if we have 5, we need 3 more terms. So electron RC minus RD, D minus E squared RE. So if you have 5 nuclei, this is what you have. You have a Hamiltonian that is more complicated. It has all 5 nuclei there, and then you have to solve that. And then so how does it affect the energy levels? So it comes from the solution of the Schrödinger equation. So you have to solve that Schrödinger equation. You get a different value of the energy, and that's your other level, your other energy level. Adam, does that help? Okay. If not, type into the chat. But this is how, if you want 5 nuclei, we just write 5 nuclei. Perfect. Okay. Very good. Ask questions. I like that. All right. Good. So now, what I'm just trying to say is, what we're now doing is we solve this equation that we just looked at. We plot the energy that we get from this, and we do that as the function of the distance. So let me close the chat, otherwise I don't see my screen. Okay. So let's say, for instance, the one that we solved here, let's say this one, we have a certain distance here. I don't know if maybe blue is not a good color for this. Let me make this green. Yeah, like this. Okay, so this is our distance. The distance between the nuclei. Okay. In this plot, we chose one value what the distance is. Okay, so we take that, we compute the energy from Schrödinger equation, and we plot it. So let's say, sorry. We plot it as the energy that we get from Schrödinger equation as a function of the distance, and from that solution that we just did, we get one value of the energy. Let's say this. And now what you can do is, you just say, in my next plot, I change this parameter. I bring the atoms closer together, or I bring them further apart. And every time I chose a new distance, I get a new value of the energy, because the Schrödinger equation gives you a different value of the energy, depending on the distance. Okay, so that's exactly what we do now. So let's do this like this. So we have one value here, then we bring the atoms. Do you guys want to bring them closer together or further apart? Who wants to bring that? Let's start. Who wants to, which one? First, close together or far apart?
Close.
Very good. Good. Let's start that. Yep, perfect. So we go, I don't, like this. All right. So what do you think will happen with the energy if I bring the atoms closer together? What will happen? So let's say we bring them very, very close together. Let's say we're here.
Energy will increase.
Increases, exactly. So let's say we have a very high energy for the nuclei being very close together. If you bring them even closer together, you get higher and higher energy. Absolutely correct. Okay. Now, if you're between here and here, these two positions, the energy will go down first at some point, and then I mean, this is one of our points. So at some time we go back up again, and then we go higher and higher if we bring them. So now let's interpret that first. Why does it look like this? This is because we bring our molecule very close together, and the energy of that will be going up and going up and going up because the electron does not want to be to two protons that are so close together. And so that the electron tells you that by having a very high energy. So that's what you see here. So if you go very close, it gets a very high energy. If you move them further apart, the energy is better. Somewhere there's a minimum. And then if you bring them closer to, if you bring them further apart again, the electron also doesn't like that. And it gives you more energy. And so that is exactly the energy that we then get as a function of distance. Okay, so let me draw this. And this is what that looks like. Okay, so if we take our two, let's say we take our two protons, and at some distance they have a minimum in their energy. That's the one that over here. If we bring them close together, energy goes up. And if we bring them very far apart, it also goes up, but it does not go up to infinity because if you think about hydrogen in nature, you can have two hydrogen atoms and just take them like this. They will be fine. So they have a higher energy than this, but they will have not an infinite energy. So in other words, they have some energy, and then they are sitting at infinite distance, let's say, but they just sit there. So this is the behavior of this energy versus distance, energy versus distance. Perfect. That's exactly, we almost have forces. We're very close. Right now we just computed the energy. So then we have, there is a repulsive term. So it pushes the atoms apart, and this is an attractive term. Attractive, and that attracts the two nuclei together. And somewhere here is our minimum. Minimum. Perfect. Okay. And so now I'm gonna, okay. Any questions about this? Because on the next slide, I'm just gonna write down this as an equation. We look at some numbers, and then we take this and turn it into forces on the next step. So any questions what I did here? Oh, sorry. Any questions about this? Anything? So you see how we went from this, where we have a Schrödinger equation, and we compute the energy from that Schrödinger equation, and then we have a parameter, and we solve many Schrödinger equations. So for each distance, we solve one Schrödinger equation. Do you see how I treat differently the electronic position and the nuclei position? One of them is in the Schrödinger equation. So the position of the electrons is here, and in this case, we have an external parameter, which is the distance between the atoms. So any question about this before I go to the next slide? Does that make sense? Okay. Okay, then let's look at what we now have. So we have one single Schrödinger equation, and what I just said is for our H2 plus molecule ion, we write this equation a little bit more complicated, and that is H with a parameter capital R. So this is this guy, right? And then it depends on the electron coordinate. The electron, that's the Schrödinger equation that you solve, and it has a wave function, has a parameter of the distance of the nuclei, and it depends on the electron of the electron coordinate, and that is equal to energy versus with a as a function of the parameter times the wave function. So that is our That is our Schrödinger equation that we want to solve. Because we need to solve the Schrödinger equation, but we have a parameter which is the distance. That's all I'm going to say, actually. So everything I said on this slide, I just wrote that now here as an equation. Okay. The last thing we now have to do, so now this is sort of like an example. So if we want to do this, everything I did here as a cartoon, I just drew it with my pen. You can do that numerically. So in other words, you can take, we say this equation, and then we use a Schrödinger equation solver that gives us these energies here, and we plot these data points, but they are now numerically correct. Like we can, we solve a Schrödinger equation numerically, and we get actual numerical values of the energy. Here it's just an image and a picture. Here we have actual numbers, right? So that comes out of the Schrödinger equation. I cannot do that by head, I know, just in my head. So I have to solve that on a computer. But the idea is exactly the same. We do exactly this. We put the protons at a certain distance, we compute the energy, we put it at a different distance, we compute the energy, and so on. So this blue curve comes out of a Schrödinger equation. Exactly the same. So I have not really much more to say. This is just quantitatively correct. This picture here is qualitative, and this is quantitative. All right. Okay. So this is an intermediate summary. So what we've done so far is we talked about nuclei will be classical, electrons will be quantum mechanical. We solve a Schrödinger equation. We looked at our wells and everything. And then we introduced the parameter. Okay. And that gives us, in this case, an H2 plus molecule. Okay. Now what we're going to do is, and goes a little bit faster because the rest is doing the same thing, just with more atoms, which makes it more complicated, but complicated for the computer and not for you. If you have understood what happened here, the rest is more complicated numerics, but the computer solves that for you. The physics and the feeling what's going on in that problem, at this point you can already understand it, and that is this picture. Okay. And then, so I'm going to show you that, a more complicated example. What does it look like in a solid? Right now, it's just this molecule. In a solid, it's more complicated. I show you that picture on the next slide. And then we do a couple of examples with density functional theory, and then we're already done. So if you understood this part, I think you understood the essence of forces in a solid even though we just looked at a molecule. Okay, so then let's look at this real quick, and then I take questions before we go to forces. So now, as you can see, and that's why I took images here that I plot with a computer, because it's too complicated to draw with my pen. But the idea is exactly the same. The y-axis or the z-axis in this plot is the potential energy. I can zoom in here a little bit, actually, like this. So we have an axis here, that's the energy axis. And then we have more complicated. So maybe let me jump back one more time. Here we only have one axis, okay? Because we only have two protons. There is just the distance. They don't care in which direction they are, and so on. If you have, of course, let's say, for instance, 4 carbon atoms, it's more complicated. You have more atoms, so it's more complicated, and you need more axes here to make these plots. But the idea is exactly the same. And then you compute the energy for each value of all the parameters that you have. And then you see some parts that are high in energy, so the atoms do not want to be there. But then we have a minimum here, a minimum here, a minimum here, and a minimum here. And those different minima, all of them can exist in nature. And these are different configurations of this arrangement of the atoms. And they give you a minimum that can exist. And maybe some of them is the absolute minimum. Then it's the lowest one in energy. That's fine. But the idea and where they come from is exactly the same. So this is the potential energy surface. So what we drew here is this potential energy curve. When you read somewhere about a potential energy surface, it's exactly the same, except that we have more complicated numbers of atoms, not just two. So maybe I'll leave this up here for a second. If you have a question, that would be a good moment for that, I would say. Okay. And I should also say, the idea here is exactly just like we did in this plot, where we have one data point here, one data point here, and these 5 data points. It's exactly the same here. We have we just sample this surface. We put a lot of data points here, we compute the energy, and then that allows us to plot, you know, this colorful thing that you can plot. But the idea is exactly the same. You simply compute energy solutions for different values of the positions of the atoms. So these guys here. So it's the same parameter, capital R. Any question about that? So we're now done with energy, and we go to forces next. Because that, if you understood that, forces is a tiny step. You'll see that on the next slide, on one slide actually. Any question? If anything is unclear, now is a perfect time to ask, because after that we look at forces now.
For the energy, it's always the local minima. It's not the...
Well, so what you find in experiment, yes, I think so. You can find the minimum, but let's say, for instance, if this minimum and this minimum are very close, then it can absolutely be that 50% of what you find in experiment is this, and 50% is this. Just because the energy is very close. They are small, they are still minima, local minima, but they can both exist. They can both exist. And if you hear different, different configurations of a material, let's say, for instance, the FCC and the BCC phase of a material are very close in energy. That means in some experiments you will find FCC, and in the other experiments you find BCC.
Okay.
So that can happen.
Because I also do experiments.
Yes.
Yes.
Exactly. So if they're energetically very close, these different arrangements of the atoms, for instance, if those are very close in energy, then you can find them all in experiment, I would say.
Okay. Thank you.
Yes. So Fatima says exactly in the chat. So meaning having 2 configurations, precisely. So there are, in particular, so we will look at solids in a moment, and we started with molecules, but that's in some sense the same thing, just how the atoms are arranged. And if you have molecules that have 2 different configurations, maybe the energy is very close, and then both of those molecules, both configurations of those molecules exist. Can absolutely be the case. Exactly. Okay, so then let's look at, so with the time we have, maybe I would say we do maybe like 15 more minutes, and then I take some questions, I would say. Okay, so how do we get to forces? Now, again, I talked about forces the entire slides, the entire lecture, and we have not seen a single force. The problem is forces are now very simple, because this is the idea. So if you have understood how we compute the energy, and that's what we spent the entire lecture on so far, computing the energy. Once you know how to compute the energy, the only thing that you do is to take the gradient of that, and you get the force. And that's it. So this, going from energy to forces, is simply taking this energy, put this potential energy surface, and take the gradient of it. And that's it. Because then you have forces. And what you see here is now, if you go back to my simple picture, hold on, I'm trying to find it. This guy. This is our energy. If you take the gradient of that, the gradient of that, you take the gradient of that and plot that, and that's it. And then you have the force. And that's all. So in other words, we have the same idea. There is an attractive force, there is a repulsive force, and the force is somewhere 0. When the force is 0, the molecule is happy. When the force is 0, so that's why we call it R0, because that's the distance at which the atoms want to be. So that is right here. If you bring them closer together, they repel each other. If you bring them if you bring them further apart, they attract each other. That's it. So there is nothing other than taking the gradient of the energy. So if you understood the energy, the force is actually relatively simple, and you can do that numerically. So that's why I didn't discuss forces so much, because it's really simply the gradient of the energy. And how you would do that numerically, you take these data points and you compute the gradient with a routine that solves for the gradient, but there's no other physics in there. You just compute the gradient. Okay. Any question about that? So otherwise, yeah, that's why I didn't say much about forces. What we oftentimes care about is really the energy. Okay, so then how do we go now? How do we turn this into something practical? Okay, so that's, I think, what the rest of this lecture is meant to be. So what we talked about is this molecule. We looked at more solids. I think those we just discussed. The next point is in practice, you have to somehow compute this energy, right? So this stuff you have to get from somewhere in practice, and you have many or several choices that you can use. Either we can do a full Schrödinger equation. That is usually too complicated, as we discussed. Like for very few electrons, it's too complicated to do. So we need approximations. Now, density functional theory is one of the approximations that we can use. In this lecture, we're not discussing density functional theory in detail, but it's an approach that we can use to get the energy. So that's exactly the same energy that we have here, and we can take the gradients. So density functional theory is practically used in many, many examples. And so then, yeah, we write our Hamiltonian, we solve the Schrödinger equation, and we plot the energy. In practice, we oftentimes say we take the Hamiltonian. Instead, now we make approximation and we solve the Cohen-Sham equations, because we do density functional theory. We solve these Cohen-Sham equations, and then we do the same thing. So then we do instead here. So we're sort of like replacing solving the very complicated Schrödinger equation, and we solve that instead with density functional theory. But that's just an approximation of the same thing. And the other advantage is this is implemented in software that you can download, like Quantum Espresso or VASP or any of the other quantum density functional theory codes, and you can do this step by just downloading the code and running it. But then the idea is the same. You plot the energy and you compute the force as a gradient. Okay. So now let's look at... Okay, yeah, go ahead.
Sorry, I just have a comment here, because we just finished the calculation for the SCF, and we got the total energy for different systems. So what I wanted to say is this is the same total energy that Andrew actually talking about. Calculate forces, all you need to do is just to take the gradient for that energy, and then you'll get the forces.
It's exactly the same. It's precisely not just in words the same. It's actually the same. It's the same energy that comes out, exactly. The only thing you have to do is to plot either this or this, you have to move the atoms around. So it's, when you computed the SCF energy, you put the atoms at a certain point, and then you get an energy, then you move the atoms a little bit different, get another energy, move the atoms a little bit different, get another energy. You can, if you have a solid, you have to rotate the atoms and everything. You put them in different configurations, just like you see them here, right? You put the atoms at different positions and compute an SCF energy for each of those. Precisely. Thanks for the comment, actually. That's very helpful. Because it is really the same. Okay. All right, so then what else? Now, the rest is a little bit technical. And technical, what I mean by that is, so how do you, again, for the purpose that we just talked about, we're actually sort of done here because you can use the density functional theory code from this point on. You compute the SCF energy, maybe for many configurations, but you can do that and you get exactly what you want. A couple of technical comments are now coming here. So how do we get forces in DFT? You don't have to worry about it because it's implemented in the DFT code. But in order to implement it, so the people who wrote the code, they had to use, for instance, a theorem that's called the Hellman-Feynman theorem. And that helps you to implement that helps you to implement computing the forces from DFT. So they use this Hellman-Feynman theorem to be able to implement that into the DFT code. Personally, as a practitioner, and also my students, we don't really have to go through these equations because the DFT code already has it. But if you want to read about it, and that's why I put the slides here, you can read about it and you can understand exactly how it's implemented, but using the implementation is completely fine. Okay, so I leave that here. If you have any questions, we can discuss it later, but you don't have to implement it yourself for now. Okay, the same thing you can, so this helps you to get the force from DFT. The second slide that I just want to show you briefly is how is the gradient implemented? Again, it is already implemented for you, but if you want to write your own DFT code, you have to implement the gradient, and that requires a bunch of technical equations. And so those equations are here. So you can compute that and you get the forces from that. Once you have the forces, you can try to find, so if you know the forces that you get from DFT, one typical thing that you would do is, and I don't know if you guys discussed when you said that you used SCF, did you guys also relax forces or no? Not yet, maybe?
Actually, we are waiting
Not
after your lecture to do relaxation.
Okay, so when you relax forces, what you do is you're finding the point where the force is 0. Now, how would you do that? Well, you just change the positions of the atoms until the force that DFT spits out is 0. And that's exactly what you do. So that process is called relaxation or relax atomic positions. And what you do is you move the positions of the atoms until the force is 0. Because when the force is 0, then you're done. That's what the equilibrium positions are. And so in practice, you now have to not run many simulations yourself and change the positions every time. DFT codes do that for you. You put a certain set of atoms there, you put their positions there, and you start, and DFT finds the point when the force is 0. So that is called relaxation. We're relaxing our forces until they are 0. Problem is that can be slow. So now it depends on what you do, on two things. It depends on your initial condition. Somebody asked about the initial condition earlier. These relaxations can be very slow, and it depends on the initial condition. And it can require many steps. So it can absolutely be that you require 1,000 steps until you find the force being 0. If you have a very simple solid, you do not require 1,000 steps. But if you're looking, for instance, at a complicated molecule or a surface or something like that, it can take a lot of steps until you find forces equal 0. But that is what relaxation is. Okay, so I leave that for mostly for your slides again, because in practice you just use those techniques. You don't have to implement them yourself. The other thing is,
sorry.
Yeah, go ahead. Please go ahead. Please go
I
ahead.
have a question.
Yes. Go ahead.
There are relationship between F and T. F equals 0. That is mean T equals 0.
Yeah. The time, no. So time in this, in what we just looked at, there is no time. So in ours, is that what you asked? If there is a connection to time? Sorry, I think you just disappeared. So did you ask about the time in those simulations?
No, temperature. T equals 0. DFT is ground state theorem. T
Precisely.
equals 0 K.
Temperature.
Temperature. So temperature, we will get to temperature in a moment. Right now, there is no temperature. Right now, we're just looking at the ground state.
Okay.
If you have, so I have one, I can actually jump there. I think I have one slide. Sorry. Oh, I'll get to that in a moment. Oh, where is it now? You get all these slides. Don't worry, we don't have to go about that. Here, molecular dynamics. So if you want temperature, so if your lattice, the ions are at a certain temperature, you can do that. And what you combine that with is we solve our F equals ma, just like a molecular dynamics code. So you use DFT to compute the force, and then you solve F equals ma, and you do a molecular dynamics code with that. So you can do that absolutely. And then, but in that case, we're not looking at the minimum anymore. When we do this, we're not looking at a minimum, but we have a temperature and we sample trajectories. What we talked about so far was we're just looking at the minimum, and we're just trying to find the minimum. And you can do both, and both are implemented in codes like VASP and Quantum Espresso and so on. If you want to do that, I would look for molecular dynamics. Good question. Good question. So let me just hop back to maybe this one, I think. Okay. The other thing, I want to actually maybe briefly talk about one thing in a second. You can also find the stress tensor, like how stiff is a material. You can compute that with DFT. Approach is exactly the same. And it's implemented in DFT packages, so you can simply change the shape of the simulation cell. You compute the energy, and from that you compute stress tensors and stuff like that. It uses exactly the same thing because it only requires the energy for different displacements. Okay, that you can do. Potential energy surfaces, they come out of DFT. Okay. Now, if you have many atoms, they can be complicated, and in practice, you oftentimes do not plot these because they're too complicated to plot them, but you use them to find the minima. What I briefly want to mention, maybe there's two things actually. This one, if any one of you guys has heard of phonons, so lattice vibrations, uses exactly the same approach. It computes the forces as the derivative of the energy, and from that you can compute phonon frequencies and phonon dispersions and things like that. So in this case here, this is a band structure of phonons, not of electrons. These are phonon band structures. And where do they come from? Same thing. You use DFT, you compute the total energy, and you compute the forces, and from the forces you get these phonon dispersions. Okay. The last thing I want to briefly say, and that is, so we talked about, we look at the Schrödinger equation as the starting point, and then we go to DFT because it's computationally more affordable, so it's cheaper. What other technique can you use if your DFT is still too expensive? And then I go to that slide. I want to see what you guys think. So we started with Schrödinger equation as a solution, gives us great, accurate solutions, but too expensive in our simulations. So then we went to DFT. It's an approximation, but gives us still relatively accurate results. So what other techniques could you use other than these two?
Machine learning.
Precisely. That's exactly what it is. So nowadays we have to, what I draw here in the beginning is, if you ever heard a Leonard Jones potential, same idea, We have a potential energy and we have a distance, and then we get our curve like this, and we have a Lennard-Jones potential. So Lennard-Jones is an analytical equation. So we have an equation for the potential. So I write that equation real quick, and then we talk about machine learning. Exactly. So the potential here would be, in DFT, there is no equation for that. For Lennard-Jones, we have an equation. So it would be 4 epsilon. And we have, so this is sigma over r to the power of 12. So it's the 12th 6 Lennard-Jones. So Lennard-Jones would be like this to the power of 6. So in this case, we have an analytical equation. Nowadays, we're not doing that anymore, and people use machine learning. So they use density functional theory data to produce a bunch of energy points. And if they have a certain training data set, they use these energy data points from DFT and train a machine learning potential to make DFT faster. That's essentially the idea. But the physics is exactly the same. We have potential energy, we have different configurations of the atoms, and then we train a machine learning potential. Perfect. That's exactly. So I don't think I have a slide for machine learning, but I wanted to write that down just because it is very, very common nowadays to start with DFT, produce a training data set, train your potential, and then you have a cheaper and hopefully still relatively accurate potential and do molecular dynamics, for instance, with the machine learning potential. So I'm going to write that down here. Machine learning potential. Perfect. Perfect. Okay, and so then what I'm going to do is I'm going to upload these slides. Yeah, these are technical things that you don't really have to worry about. We talked about molecular dynamics and we talked about phonons. So I upload these two things and this one I skip. Any other question that you want to discuss? Anything that we talked about? So I think that is the end of what I had. So this is my summary. Any question that you have? What I really hope you guys, at the very minimum, I hope maybe you can follow this and this, because with this you have understood all the essence of this, and then the rest is technical details that you have to do with running DFT and stuff like that. Any question that you guys want to ask? I know we had some questions in between, but if you have something, let me know.
There is a question by Muhammad. He raised his hand.
Oh, let's see. By Muhammad, really? Go ahead. If you have the question, Mohammed, maybe you just asked it. I don't see it in my chat. I think we went over this already.
My question is, to calculate the force, I see we need to use the atomic position.
Yeah.
And computation. So since plane wave bases are independent of atomic position, are we restricted to use atomic centered basis to calculate that force?
I think it is very hard to understand. I'm sorry.
Can you repeat your question, Muhammad? Or you can also write it on chat.
Or maybe, for some reason I have some echo here and I think it's very hard to understand for me. Maybe if you want to type it, I can wait here for a couple minutes and you can type it here. That's fine. Or if somebody else has understood the question, maybe just repeat. There was some echo here. I couldn't quite hear.
Me neither. I haven't heard the question well.
Musa? I might get like some part of the question. I think he was asking, since we can compute the forces, like the total force on the atoms, can we look also at the individuals? Actually, Quantum Express or most of the DFT codes, they calculated also like the forces on individual atoms and then the total force. It's always gonna be like printed out in the output files.
Precisely.
You don't need to do like any post processing to calculate it like in each atoms individual.
Exactly. That it's in the output, precisely. I completely agree. So let me see. Mohammed type details. So since plane wave functions are independent of atomic positions, while atomic centers are restricted to use atomic centered bases. So yes, I believe yes. So if you relax positions, for instance, and your atomic centered base, like the atom's positions changes a lot, you have to update the bases, I think. Because it's exactly what you said. Because if you start relaxing the atoms away and your basis is still adjusted to the initial condition of your atomic centered basis, I think it's not compatible anymore. But you can fix that by, relax a little bit, update your basis, and keep it so that it matches to each other. But yes, I think in plane wave that is a little bit easier than an atomic centered basis. I do agree with that.
Thank you, Professor. If there is another question, if there is no, we can conclude now.
So I'll send you, maybe I can send you the slides. Is that the easiest?
Yes, you can send it to us.
Or I still have the box link. I can also upload them there. I mean, either way is fine.
Okay, and we will communicate it with the participants. There is a question also from in the chat.
Born-Oppenheimer. So that's a good question. So what Born-Oppenheimer does is it decouples electrons and ions. And in what we talked about today, all of that uses the Born-Oppenheimer approximation. So in other words, what we do is we put the atoms somewhere, leave them there, and relax to the ground state. So when would, let me see, I think I have a slide here. Yes. So this is going, hang on, you don't see the slide anymore. Hang on 1 second. Here. So that is in your slide. So let's say your atoms move around very quickly, so at high energy. So in other words, they move on a time scale that is comparable to the time scale of the electrons. In that case, you have to go beyond Born-Oppenheimer, and that is, for instance, called Ehrenfest dynamics. So you can do that with time-dependent DFT, for instance. But in everything we talked about, so this is I would say an advanced topic. We didn't do this today. I just give you the slide because all the slides that you saw today were assuming the Born-Oppenheimer approximation.
Okay, so we conclude now. Thank you so much. It was a pleasure to have you. Very nice lecture. I enjoyed it a lot. Thank you so much. And thank you for the participants. Tomorrow we will have the hands-on at 4 p.m. Khartoum time. And see you. Thank you so much, Professor Andrew.
Thank you guys for attending. This was awesome. Very nice. Thank you guys.
Yeah,
and reach out via email. If you have any questions, feel free to send me an email.
Thank you. Thank you so much.
Alrighty. You guys take care.
Thank you, you too. Bye.
See ya.
Okay, thank you.
Many thanks. Many thanks. Bye.
Thank you.